And good morning, everyone. This is our day 10 of 2-month long webinar series which C-DAC Patna is conducting on AI and data science. And today's expert of the session is Mr. Aniket Palkar, Head of Cloud and Data Science Digital Connected Solution, KPIT. Before starting the sessions of today on data science and its applications in industrial and automotive context, I'm just currently he is looking after driving technical strategy for connected vehicles with emphasis on cloud, data science, and analytics. He's also handling architecture of automotive digital systems and working with global automotive customers and teams from various other countries like Europe, USA, Japan, and also in India. He has handled large-scale data cloud-based data management in past with data farms, data lakes, and good hands-on on big data system expertise. Also, his expertise also lies in connected vehicle and mobility systems, fleet management, asset management, and data-driven intelligence. And has also have worked on driving cloud and data strategy for connected conventional and electrical vehicles and new mobility ecosystem. In continuation with our this webinar series where we are trying to cover each and every perspective and domain and how can we apply AI and data science, starting from the basics of mobility, then AI on mobility, then AI for healthcare, and now we are coming to data science and its application in industrial and automotive context. So we are privileged to have you, sir, and certainly this session would be a great learning for all the participants. Aniket, sir, over to you.
Thank you. Thank you. Okay, so good morning, everyone. Thank you for joining this session. Really appreciate it, and hopefully you all will, get some insights out of this session as well. I know there was, previous session, I believe, from Dr. Shishir Sai from KPIT as well, talking about some of the AI and ML aspects in automotive. So he's more focused around the autonomous driving side, while my focus in KPIT is more around the connected vehicle side of the house. But in both contexts, data science and data-driven intelligence is something that is extremely relevant. So, what I'm planning to do in the session today is, hopefully, give you a little bit of insight on, what are the different aspects of data science in the automotive industry, what are the different applications, and hopefully also give you a sense of why data science is so critical in this industry, and also sort of the overall scope of this industry, and why coming in with a data science analytics background in this industry is something that is going to be of increasing importance over the next few years, and this from a data science perspective, there's been a lot of focus on some of the other industries in the last couple of decades. I would say consumer facing technology, then fintech, then e-commerce, and digital services and digital enabled services. But automotive brings in its own complexity and challenges, which I believe are even more significant than what are there in some of the other industries. And so we will see about that. As far as thank you for my overall introduction. I will just add one point to it. So for the last 20 plus years, I've been working on at scale software systems and data-driven solutions in various industrial contexts. So I have significant experience working in the power generation industry as well as oil and gas industry prior to coming in automotive. And in all of those contexts, it has always been, how can we use data and data-driven intelligence in the context of these industrial systems to add more value, provide more value to business, drive data-driven solutions, and do that at scale because of the huge volume of data that each of these industries generates. So, I assume, most of you might be, learners, I would say, that since anyway you have joined this webinar, you're keen to learn, whether you're students or not. So I'll, hope to also emphasize why, applying your learning in the context of this industry is something that is going to really help you. And there are important problems that need to be solved over here. So, first slide, many of you may have heard, may not have heard, or at least have heard some of these trends. So right now, the automotive industry is really going through a massive disruption. And, we see this four big trends that are there. Commonly it is referred to as CASE, and, there are couple of other acronyms as well, but connected, autonomous, shared, and electric. And if you look at each of these trends, right, each of these trends on its own is enough to disrupt an industry. And we are seeing four of these happening together in parallel in the automotive industry. So it's a massive change. It is a once in 100-year event that is happening over the last few years in the automotive industry. And from a data science perspective, each of those are relevant, because connected is driving us to have more and more data being collected and brought into the cloud. This is enabled by fast modern connectivity through cellular networks, moving in from primarily 2G networks to 4G networks, with now technologies like 5G and NB-IoT driven by 5G coming in to have even higher speed connectivity, which enables new kinds of data to be collected. Autonomous driving, of course, a lot of work has been happening in this area. I think we probably have most of the elements of level 3 autonomy in place, and people are trying to go through level 4. Certainly, if we see companies like Waymo in United States, then Tesla have made a lot of progress. We probably have, it has probably not reached the level that it was expected to reach. I mean, certainly there were predictions that by 2020 we would be at level 5 autonomy a few years back. We don't quite see that, and probably it's still maybe 5 to 10 years away, because the challenges of resolving the issues of the last 1% are enormous, and people are trying to do that. But again, this is enabled by data, enabled by data science, enabled by machine learning, enabled by deep learning, taking all of that information and essentially to have a software drive the vehicle and replace the human being. It is one of the most complex challenge as far as AI goes, that people are trying to work on. Shared, again, it's very relevant from a data science perspective, because it is enabling new business models, right? How do we go from an environment where, rather than vehicles being bought, they are increasingly being subscribed to, they're increasingly being leased, they're increasingly being used on a demand basis as part of shared mobility. All of that needs data coming in from vehicles. All of that needs things like routing, navigation information, what is the best mechanism to navigate, any kind of logistics that we see that this enables, whether that be food delivery, e-commerce delivery, everything is ultimately enabled by vehicles of some sort. And those vehicles need to be tracked, data from them need to be collected, whether that be a two-wheeler, whether that be a four-wheeler, whether that be a commercial truck, so again, we see data science being critical. And then electric, while electric in itself might seem like, okay, it's just a different mechanism of moving the vehicle. You have diesel engines, you have a internal combustion petrol engine, and electric, obviously it's a different powertrain, different uh, uh, you know uh, way of driving the vehicle, but also very relevant from a data science perspective, because these new electric vehicles are increasingly instrumented right from the beginning. And the electric vehicle is more software and data driven as compared to the more conventional vehicles, essentially because they have been coming in new, and the latest technology is being incorporated in these vehicles. So latest ADAS technologies, parking assistance, lane assistance, a lot of things that are enabled by data and AI. So huge changes are happening in the industry, and data science and analytics is at the center of it. So next I'll just give you a sense of why, especially for India, this industry is one of the most critical industries. So as you can see, you can read some of the statistics on the right, but as you can see, it's got a massive share of the GDP, and it is also one of the industries where we are very big. We are we have a huge internal market, as well as we are also a big producer of vehicles. We also export a lot of vehicles. This might not necessarily go to the more developed Japanese or European or North American markets, but to Asian markets, to South American markets, to African markets, we export a huge number of vehicles. And it's something to be proud of, really, as far as the scale of this industry goes. And other critical aspect of this industry is, it's also something that provides a lot of jobs, because it's a very manufacturing centric industry. So it's a very large employer in the country, and these jobs are not just white collar jobs, but a lot of working class blue collar jobs. So it is making employment available to a lot of people, and that's very important for a country like us. So the impact that we have is huge, because there is a spin-off effect, and it enables a means of earning livelihood for large number of people, and this is growing. So it will move to larger share of GDP, bigger share of the job market. We still have a growing population. So all in all, it's a critical industry, and it's an industry where opportunities are just increasing. So it's a right time to get into this industry, and data science will enable that. So we talk about data science, and the main thing that enables this, as you all know, is data, right? You cannot have data science, you cannot have analytics, you cannot have machine learning, you cannot have deep learning, AI, anything, any of the buzzwords, without having data. So this is very critical, having a robust uh, data sets which allow you to understand what is happening, what is the historical behavior, what is happening today. Without that information, you cannot predict the future. Our predictions of the future are based on the current state and on the past date. So where do we get this data? Where what are the sources of vehicle data that are coming in? So one, I briefly alluded to this a couple of slides back, but one important thing to remember is, when you think of a modern vehicle, right, it is increasingly a software defined system. So when we think of a computer, we think of a mobile phone, like a smartphone these days. We realize that it's primarily a software defined system. While there is hardware over there, it is a software that is doing the differentiation and providing most of the value. What sometimes some people might not realize is that that's true of modern vehicles as well. It is no longer just a mechanical and electrical system. While those elements are there, and especially in an electric vehicle, it becomes even more even more software oriented. So a typical vehicle, as a result, will have lots of microcontrollers, lots of hundreds of microcontrollers driving ECUs, whether that's a engine control module, whether that's the ECU that is responsible for the anti-lock braking system, whether that's related to more mundane and prosaic stuff like maybe headlight control, or it could be like door control, locking, unlocking. There are literally hundreds of these microcontrollers, and tens of thousands, hundreds of thousands of lines of code that is really driving the vehicle. And in a many sense, it is a data center on wheels. It is huge amount of data is being generated. So we the most common and obvious one is like data that is coming from sensors. So this could be things like temperature sensors, pressure sensors, for the various consumables that could be there or that will be there. Let's take engine oil, let's take brake oil, let's take coolant, let's take air conditioning system, as well as some of the data that is generated by the various ECUs and components of the vehicle itself. This is typically available on the canvas in the vehicle. It might be publicly available, for people to look at, for through things like the OBD port, onboard diagnostic port, or it might be proprietary, but it is there. And it also includes things like diagnostic troubleshooting codes and so on and so forth. Then, in-vehicle infotainment system, we don't think of this sometimes as a sort of a core component, but from a consumer perspective it is critical. A lot of people will look at what kind of a IVI system is there with the touch screen, and what ability it has, and there's a lot of content that is there. This content is also data, embedded navigation, embedded maps in the in-vehicle infotainment system, that is also data. And there are trends and patterns that are coming out of it that also needs to be analyzed. What is your most frequently used route? What is the most optimum route? What can the vehicle learn from the fact that you leave your house at certain time during the day, and you reach a particular destination? Could be your office or your college, or wherever else, right? So a lot of data is there. Then GPS, very traditional source through things like the telematics control unit. This is particularly critical in fleet applications, or any kind of logistics applications, being able to track the vehicle where it is, and also be able to track things like speed of the vehicle, acceleration, braking, through things like magnetometer, accelerometer, gyroscope sensors that are typically embedded in the TCU. So that's another source. And increasingly with autonomous driving, other data sources are coming in. So cameras are increasingly critical. All autonomous vehicles will have cameras to essentially serve as the eyes of the vehicle. There's also internal facing cams, dash cams. A lot of these are generating data. These can be critical, for example, in generating data that is relevant to accident events, and inform insurance companies about that. And then LiDAR, radar, again from a autonomous context, being able to use either traditional radio waves or lasers to accurately detect and figure out what the object is, where the object is, so that the autonomous vehicle can sort of navigate and drive itself. And so some of these vehicles generate up to like 25 GB an hour, and with autonomous this is going to go really in a way out of control, right? Huge amount of data. And this is just data that is coming from vehicles. You have other data, data that is being generated through the design and development process, the vehicle production process, the ownership of the vehicle, that generates data as well. Who owns the vehicle? Do they have, when did they renew their insurance? What's the pollution status of the vehicle? When a resale happens, how that gets tagged, how the people are using it. Are they is the vehicle owner using it well? Are they driving it harshly? Are they driving it in normal conditions on good roads, or they are driving on bad roads? What sort of terrain they are driving? All of that is important, because that is going to have an impact on the lifetime of the vehicle. These are machines which people expect to last at least 10 years, if not longer. 10-15 years minimum, and in some cases even longer as well. So it's not something that like a mobile phone that you change in 1 or 2 years. Once a vehicle is out, it's going to be out there potentially for 20 years, and it has got to keep working well. And when it fails, it can threaten lives as well, right? So failures are not acceptable. And then of course maintenance and repairs, periodic service, periodic maintenance, repairs, what changed, which component had to be replaced, which consumable had to be topped up or replaced. All of that is data, and a lot of that data is then sitting in different places, right? It could be sitting with the dealership, it could be sitting with the service center. people might not always go to an official service center, so it might be sitting with small garages. How do you sort of use and collate that data and derive intelligence from it? That's also critical. um, and with all of this data being generated in the vehicle and outside the vehicle, to really enable data science, to really enable machine learning and other techniques, or it could even be simpler algorithms on top of that data, or business intelligence and visualizations on top of that data. What enables it is really the connectivity. So there's when we think of vehicles and automotive today, we should not just think of vehicles. We have to look at the whole system, which includes the world inside the vehicle and the external world, and that external world is increasingly today sitting in the cloud. Whether that cloud is used to bring in the data to run analytics, whether that the cloud is being used to run as a backend of apps, whether that be an app that is as part of the vehicle for the driver, whether that be a logistics app that is being used by your e-commerce delivery person, all of that is working off a cloud backend. So this whole system needs to be in place to really enable data science, and that is being enabled by the connectivity aspect. And connectivity costs, as you all well know, have been decreasing, and we've seen it's going to fall further and be faster now with launch of 5G starting to happen in certain markets. So like Korea, Japan, United States, 5G networks have already been launched. At some point of time that will also start migrating to other markets, and we will see that in our markets as well. It might not happen immediately, but it might not take as long as we might expect. Certainly in the next couple of years, we'll start seeing those high bandwidth 5G networks as well. I think it's a good segue anyway. I'll just maybe pause for a minute to see if there are any questions on the material so far before I go to the next part of it. Anyone has any clarifications that they want to ask? All right. So if nothing so far, we will continue. Hopefully, it has been it's been quite clear so far. So now this we spoke about the data that needs to be collected, different sources of data, different types of data that these vehicles are generating, the cellular networks, and the next question becomes when we build, whether it be just a simple algorithm or whether that be a machine learning model, whether that be a deep learning model, where does it execute? Where can it execute? So there is a couple of different areas over here. So, over the last, I would say, few years with good connectivity, especially since it started being enabled by 4G networks. But even before that, even with 2G networks or GSM networks, a lot of data like GPS data or sensor data, it is not a huge bandwidth of data. You're essentially talking about just like a floating point value for a sensor at a given timestamp, or a similar way for GPS, just a lat long, right? So it's not like you're trying to transmit a video file. So even with 2G networks, which have been extremely cheap for the last 10 years or so, a lot of data has been brought into the cloud. Especially on commercial vehicles, connectivity is very common. It is becoming increasingly common now on personal vehicles, but certainly fleet owners, logistics owners, they want to track exactly where their vehicle is in the course of goods delivery. A lot of these might be carrying expensive cargo and important cargo and so on and so forth. And with the data being brought into the cloud, we've mostly been running models, ML models, algorithms in the cloud, and these then enable passing on this information or this intelligence to apps, whether that be dashboards, whether that be like mobile apps and so on and so forth. But now we are seeing a trend where On the cloud side, there was always some gap, I would say, because some latency sensitive applications cannot be executed on the cloud, or it's at least difficult to execute. If you're running a machine learning model that is driving your AI for autonomous driving, and it needs to take a split second decision on an object, those need to be real time decisions, and you cannot not have that decision taken because you have a connectivity issue. You lose network, or because of latency and variableness of the signal, for example. Because in a vehicle, while for a lot of other industrial uses like a power plant, for example, or oil and gas refineries, which are other areas I worked on, you can always run a fiber optic cable to take your data. You don't have an option of doing that in a vehicle. It has to be necessarily a wireless connectivity, because it's a vehicle ultimately. What we see a trend is to increasingly also execute these models at the edge, that is close to the source of the data. That's essentially what edge means. And what we see is that the edge is becoming more and more capable. So we see this trend in multiple ways. One way that we see is that a lot of the vehicles today, they have a lot of these discrete ECUs, right? So the ECUs are, if you're not familiar with the terminology, these are just microcontrollers that are controlling different parts of the vehicle, right? And these ECUs tended to be, very small embedded devices with, very minimal, like running very small RTOS kind of systems. And now a trend that is happening is actually putting a high performance computer in the vehicle itself. So the new vehicle architectures that are being evolved, and we work with a lot of customers, particularly in Europe and North American market, who, as they are designing their next generation vehicle platforms, are increasingly putting high performance computers in the vehicle itself. So the idea is, instead of having 100 microprocessors running 100 instances of RTOS, or maybe like AutoSAR OS or something like that, AutoSAR based systems, they will have a single HPC, and these ECUs will essentially become like, you can say, apps or services or containers on top of this single HPC. What that also means is that now you have a lot of compute to actually run your complex model. Your neural network, for example, can run and converge. Your model retraining pipeline can happen inside the vehicle itself. The other area we also see is that this TCUs, which used to be very cheap and very tiny devices just collecting GPS information and acceleration braking information, they're also becoming more complicated and beefier. They are becoming, may not be like HPCs definitely, but they are at least becoming like Raspberry Pi class devices. So rather than run a very small RTOS, they can increasingly run a 32-bit Linux operating system at least. So you can do a lot more. You can, for example, run a ML model in a Docker container on the TCU itself now. Then other areas is, we have very beefy IVI systems with touch screens, playing music, doing navigation, having embedded maps, those kinds of things. So IVS system itself can be leveraged. You can run some compute on the IVS system to do your algorithm locally. And last but not the least is sort of a fusion of the mobile and the vehicle. So one of the things that happens is, as I said, you don't replace your vehicle every 2 years. You probably use it for 10-15 years maybe, or even if you use it for 5 years, you sell it to somebody and they use it for another 5 years maybe. But you change your mobile phone maybe 1 or 2 years later. So the mobile phones are, in terms of compute, are increasing at a much faster rate, and that's bound to happen because you have a faster hardware replacement cycle. And these phones can connect to the vehicle. It could be like just a Bluetooth connection, or it could be like a Wi-Fi direct connection or whatever. So one of the things that vehicle makers have been thinking of is, if you have such a powerful mobile phone today, with like 12 GB RAM and 8 core CPU and all of that, can we use the user's mobile phone to run some of these models, right? Establish a data connection through a Wi-Fi or a Bluetooth to the mobile phone and offload some of the compute to the app. So maybe when you buy a vehicle, you also install the vehicle maker's app and the vehicle, when it needs, can actually offload some of the algorithmic and model computation onto your extremely powerful mobile phone, and leverage that. So we are seeing this as a trend where increasingly models are being run here, while they continue to be run here also, because there are unique things that you can do over here. And one of the unique things that you can do is, if you need to run your machine learning model across multiple vehicles, like a fleet type scenario, being able to see what is the comparison, or what is the difference between the model running in one vehicle versus the another, or with one vehicle's data versus the another, or what's the trend across like 10,000 vehicles. You can't run that in vehicle. You have to run that remotely for looking at trends across like a fleet of vehicles, basically. So that's where we see things moving in terms of how machine learning is evolving in the automotive context. This is like a typical, I would say, data science operating system. Now when I say operating system over here, it means more like an organizational operating system, or way we organize and manage things, not like a computer operating system. So don't confuse it with like Windows or Linux. It is more of just as operating system manages processes, this is for managing organizational processes, right? So these are the areas that we see. Whatever you build from a data science perspective, you got to make sure that it is domain relevant. So that's where you need domain expertise in terms of your organization and in terms of your team, because you got to make sure that your result is valid in the context of the domain. Then data science, this is the area where we build machine learning models, deep learning models. We use all the different techniques, build let's say regression models or classification models, all of the things that you might learn as part of a typical data science course. However, data engineering is also a key skill, and I want to highlight that. This is where you really are working on getting the data right, cleaning the data, ensuring data quality, making sure that it is sort of ready for some intelligence, removing garbage, because if you have a lot of data, that is good, but you have to pick out what is the relevant data. You have to pick out what is the clean data. If there's a lot of null values or a lot of irrelevant stuff in there, or the right stuff is not captured, it is not going to be useful. So there's a lot of work that happens in this area also in the industry. And so from an industry awareness perspective, while we talk a lot about this area, we don't talk a lot, but I would say 80% of opportunities here, and 20% of the opportunities here, if we confine ourselves to the data side. And then of course you have the deployment side. Whatever you build, right, this is industry, right? So you have to make sure that actually goes into production, it gets used. While we do a lot of research, while we try to figure out new techniques and trends, applications are critical in the industry. So you got to make sure that what is built doesn't just sit on a desktop, it actually gets deployed in production. So that is where cloud comes in, and I have not specifically mentioned it over here, but these days increasingly edge expertise, embedded expertise also comes in to make sure that it is actually being pushed out to use. Now next, this is I'm sure you must have heard of a lot of these, and I know there's been a couple of sessions already, like on autonomous driving areas and all of that. But these are the key areas that I see. This is kind of my view of the world, where I see in automotive what are the different application areas. Predictive maintenance we'll talk more about, but this is essentially using data to make predictions of component life and consumable life, and condition of the component. Autonomous driving, I believe you guys had an earlier session, so and I think everybody is aware, a lot of attention. When we say connected vehicle, right, because the vehicles are connected, it is enabling a lot of use cases. So here you'll have use cases like asset management, fleet tracking, logistics, navigation. All of these are data enabled use cases. Then we spoke a bit about infotainment, right? So one area I would like to mention in infotainment is increasingly vehicles are coming equipped with these AI assistants, right? Things like Alexa and Google Assistant and Siri. These might be, running on your phone connected to the vehicle via things like Apple CarPlay or Android Auto, or these could be running in natively, right? These assistants, goes without saying, are enabled by AI. And I put it separately because increasingly there is also a trend for security, privacy, as well as connectivity reasons, to do a lot of computation of these AI tasks on the infotainment system itself locally. That's why I've put it separate from the connected vehicle, although it might be backed by a cloud system as well. Supply chain optimization, again, if you have a good idea of uh, you know who's buying the vehicle, when are they buying it, what is the demand, what is the a failure rate of parts, which parts are going to need replacement, which parts are getting replaced out of warranty. If you have all of that data, then you can build models to really optimize the supply chain and make it better for the business, right? The business can run optimally at better cost. Customer acquisition and relationship, figuring out what do the customers really want, what are the trends, which features of the vehicle are they using, right? In the years gone by, automakers had no idea. Once vehicle was sold, it was sold. What are people actually using, what is their driving pattern, do they use it mostly in the city, or they are using it to also go out of the city, are they using it on the weekends, on the like mountainous terrain, when they go out hiking, or it's all just used for office work, or going to office, or are they using it in heavy traffic or not? Based on that, you can tune the vehicle. You can make the fuel economy better for certain use cases, or you can add and target specific usage behaviors, I would say. As also maintaining the customer relationship, because people are getting used to having their phones UI changing, and each phone is better than the next one, and TVs are increasingly smart TVs, and people are used to getting software updates, so they expect software updates and new features every year in their in-vehicle infotainment system also. And it's no longer the case that you buy the vehicle and 10 years it's going to remain the same, 15 years is going to remain the same, because if you have some UI today, after 5 years it's going to look really really bad, because technology would have moved forward. And so that continuous relationship with the customer is important, and again data enables it. And then business optimization, it's again with all the data collected from different data sources, how can you sort of make it better for the business? So my I don't think we have a lot of time left, so I'll kind of breeze through this quickly. This is kind of more of a use case. So out of all of these areas, my area really focuses predictive maintenance, and this is a huge area. So this architecture kind of depicts how typically predictive maintenance works. So this is a machine learning driven solution, and essentially what you're trying to do over here is you're instrumenting the vehicle, collecting data from a lot of sensors. You're also collecting other information that is outside the vehicle. So based on the location of the vehicle, I can figure out the driving terrain. So I can map the location of the vehicle to external data like maps data, and figure out what is the terrain. Based on looking at things like accelerometer, magnetometer, gyroscope, I can figure out how's the driver driving it, speed and all that. Are they overspeeding, are they doing too much braking, too much acceleration, taking harsh sharp cornering and all of that. Also driving conditions, based on timestamp and location, I can know, was the temperature 40 degrees, 45 degrees, was it raining, and all of that. So essentially what is happening is we take all of this data, we bring it into the cloud, and we essentially run a digital twin of the particular component. So this could be, let's say, engine, this could be a consumable like engine oil, this could be a brake. You run a digital twin of that, and that digital twin tries to mimic what might be happening to the component over here. So that is a machine learning model that is running. And typically what you try to do is you run an ensemble of models. So you will run multiple regression models as well as multiple classification models. So the classification models might only try to classify the current state of the component. Is it good? Is it bad? While the regression models might actually try to predict a specific value, like what is the remaining useful operating hours that are left. And that drives sort of predictive maintenance. And that's a very fundamental sort of a use case enabled by machine learning, because then on top of that you can do n number of these things, right? You can do better inventory management, you can do preemptive maintenance, you can do maintenance scheduling, you can figure out which in warranty parts are possibly going to fail, and be able to manage that process better. You can manage your parts availability better. So that fundamental predictive model, that digital twin that you have, is going to enable a huge number of use cases. So in an automotive context, this is a hugely significant area using ML for predictive maintenance. So we have very short time left here, and there's just a couple of slides. So I'll just pause here for any questions, so that we can cover a lot of time on this because I spoke, but the fundamental idea here again is that for predictive maintenance, you have your ensemble of machine learning models, again a combination of regression and classification models, most likely using different techniques. It could be it could be like a random forest, it could be like a neural network based model, whatever it is. It doesn't matter. Ultimately you have to choose, you have to look at the data, you have to select the right fit model, you have to evaluate it, you have to look at the accuracy, you have to look at the fit, you have to make sure that it is generic enough, and then you have to select it. And all of this data is feeding it. Vehicle parameters, we know this is typically stuff like things like for example, it could be brake position, it could be oil temperature, oil pressure, those kinds of sensor values. Diagnostics data is the vehicle itself is capable of detecting faults, and it typically produces, some of you at least hopefully are aware of DTCs, diagnostic trouble codes, which indicate what sort of issues might be happening. This is internally detected, emanating from let's say an ECU, for example. And then add to that things like service data, right? When did a particular component or part get replaced? When was, for example, the brake pad replaced? When was the clutch replaced? When was the oil topped up? When was the uh, coolant topped up, perhaps? When was the AC serviced? A lot of that information that's going to have an impact, because if you're measuring something, you're measuring the oil temperature and you don't know that the oil got replaced, you're going to get strange results. It's important. If it was topped up, you need to know exactly how much was topped up. If it was replaced, you need to know exactly when it was replaced and what replaced it. Was it a synthetic oil? Was it a semi-synthetic oil? What it was, right? And so all of those feed into the model, and then the model will produce an output, which will be a advisory in the form of how much remaining life is left. When is the component essentially going to fail? This could be in the terms of number of useful hours left, or it could be in terms of the number of kilometers left. And then the point is, if you give and this is generally true for any machine learning model, any model that you build, right? It could be in automotive context, it could be in predictive context, or always remember that if you give out a result, people may or may not believe it, right? If you say that, look, based on this, I believe that the engine is going to fail, there's going to be a catastrophic failure. Let's say a piston seizure is going to happen in the next 100 hours, and you better go and service it. Then that's a problem, because if you need to service the vehicle, you are not going to be using it. You need to give it to the garage. And if you're an individual user, maybe it's okay, but if you're like a fleet operator that needs to take a important good from one place to the other in the country, taking the vehicle out for a day is not a easy decision, right? That costs money. So you need to be able to not make it a black box. And so these models, we always make sure that it also tells you why it is doing it. And even in other contexts like autonomous driving, it is extremely important that the AI is sort of explainable. If AI takes a decision in the context of an autonomous vehicle, let's say, then it's very important to have that insight and have that visibility into it, right? Because that goes down to having trust in the system. Few months back, we had this incident where, in the US, in one of the states, where one of the autonomous vehicles from Uber got into an accident. You might have read about it, right? So I'll not talk more about that incident. You can, if you're not familiar, Google it. But essentially, when any kind of a thing happens, it's important to have that insight. And the model needs to provide why it is saying what it is saying, right? It cannot be a black box. And then the other aspect of it is, we need to evaluate multiple models. We need to figure out, given the context, given the data, given the problem that we are ready to address, what is the model that is going to be a best fit, for every problem, even if it's in the general area of, let's say, predictive maintenance, or vehicle related insights. You cannot use the same model. So it's important to be able to quantify that, so that you can select the best machine learning model. So don't lose sight of that as you're building models. Make sure your model gives the result. Also make sure that it explains the result. It gives an insight into why it thinks this is the right recommendation. Is it right? Is it biased? And also, don't be happy if you choose a model and it gives you 90% performance. See what is the best fit. At the same time, make sure it is generic enough and it's not over fit for a particular case, right? So this is another sort of, I just taken as an example, another area where it works very similar to predictive maintenance. This is again a application of machine learning in the automotive context, where it is not as easy, let's say, to be able to accurately predict the range for electric vehicle batteries as compared to the way we do with the petrol or diesel engine in terms of the mileage, right? Because a lot of factors sort of drive what range you can get. And today, at least, the charging infrastructure, although it's getting better in Western world, it's not quite there yet, right? So people have a lot of this range anxiety, because today, if you see, there might be 1,000 petrol stations in a district, but there might be like only one place where electric vehicles can be charged. Or maybe people that have electric vehicles are just using like home chargers, right? Which means you want to make sure that you've not taken the vehicle somewhere outside and it runs out of charge, because that's going to be a problem. And that's one of the things that's also stopping adoption of electric vehicles, right? People have that concern. Okay, if I run out of charge, if I need to go outside the city, to another town, and if I run out of charge in between, or I run out of a charge in a village, where will I do the charging? So giving that, making that infrastructure available is of course critical, but also giving that advisory is also critical. And this again is a model that uses all the factors that will impact the range. How is the driver driving? That is going to have, a driver that drives at a faster speed, or drives maybe more, let's say, harshly, it's going to give a different range. Whether it's a city road, whether it's traffic, whether it's highway, whether it is hilly terrain, the route profile is going to lead to a different range. Environmental conditions, ambience, temperature, and other things are going to have. Then as the battery ages, typically life of a battery might be 5 to 8 years, lithium ion battery. And as the battery ages, is going to have a different range. A fresh new battery today versus one that has already been used for 3 or 4 years, the range is not going to be the same. As well as operating conditions of the battery itself in the vehicle, dust, temperature, all of that. So all of those things will be taken into account, and they will be fed into the model. And then it's also important to have a retraining pipeline, where as new data is coming in, this model is also learning, and sort of it is getting updated continuously. The model also needs to be revolved, and these models sorry, the model also needs to evolve, and these models are increasingly also being deployed right into the vehicle, that we spoke about on the edge. Because if you have a cloud dependency, you don't want to find out that, okay, you are in an area where there's no connectivity, and now you cannot find out the range. So there are some things that could be computed in the cloud, but it's also important to have a lot of local computation, so that you reduce that dependency. And so this kind of model depends on being able to predict things like the state of health and the state of charge of the battery. And of course there are traditional methods, things like coulomb counting and other things you might have heard of. Those are also valid, but machine learning techniques, and in particular we've had a lot of success using like deep learning techniques to give better insights onto this. So lastly, I will just conclude with a few things before I open up for your questions. And these are the kind of takeaways that I wanted you to have, because it's not possible to teach you machine learning or predictive maintenance or deep learning in a 45-minute session. But the takeaway I want you to have is how data science is critically important in this industry, and what sort of opportunities this industry is bringing, because not everybody might be aware of it. People might be thinking about fintech, they might be thinking about e-commerce, they might be thinking about other industries, but this is an industry where there is massive scale, and there's a need to solve some of the world's most complex problems. Autonomous driving is the most complex AI problem of our times. If we get an opportunity to work on it, we should grab it. It is the vehicles are software driven. They are no longer mechanical and electrical pieces of equipment, and so that's where data and data driven techniques like ML become critical. Then it's a time of change in the industry. It's a very disruptive time, and disruption always attracts new players. You might have seen Apple is in a partnership with Hyundai, and there's been this talk, whether true or not, about an Apple car eventually. Google of course is right in the middle of it. Waymo, there's a lot of other high tech players that have been looking at particularly autonomous driving and getting into this space. A lot of churn happening as a result of that. New sensors, connectivity, and new demands, it is driving lot of data to be available. We already saw the scale of some of that data. We're talking about terabytes of data starting to get generated every hour from a single vehicle. Now what do we do with that data? How do we process it? How do we use it? What are the AI, ML, data science techniques that can be used? So it's an industry that has significant opportunity for data science, AI, machine learning, deep learning. And then more than that, it's also an opportunity to have a significant impact on the world, because none of us are not touched by this industry. You go to a even in any place, the smallest of place, people might possibly not even be using mobile phones, or they might only be peripherally be aware. They might not be aware of e-commerce. They might never have used a credit card or be aware of fintech or online banking. They've certainly used some sort of a vehicle. We all need vehicles. As well as it is an industry that is significantly important for us as a country, because of the GDP impact, because of the employment that it generates. And it generates, as I said, employment across the scale, right from manufacturing jobs to high tech jobs, right? So it's critically important industry, with data science playing a huge role. And I want you to sort of leave with that message and be excited, and look at the opportunities, because where else you will get to work with so much data and solve the most complex AI problem of our time, where the best minds from companies like Google, Apple, Microsoft, Amazon are trying to solve it, and all the other names that I might not be taking. So with that, I will conclude my discussion, and I will open up for any other any questions that you have. And I do apologize, I took 10 minutes longer than expected. Sorry about that.
Thank you, sir. And I think this 10 minutes and this whole session was less seeing the, even myself, I'm seeing the significance of this particular domain and AI and the data science role in this. For all the aspirants who are coming into this field or who are already working, it is huge. And my takeaway was those two slides where you explain very broadly the dynamics of automotive and all the parameters through sensors what we take and how the data science plays a role and how the huge amount of data is needed and how we apply to a best fit model and then conclude something. Thank you, sir. It was a great session and it was really a great learning experience for me and I certainly hope for all the participants. Thank you very much, sir.
Thank you.
And now I'm requesting all the participants, if you have any questions, you could ask on chat or unmute yourself. If it is okay, if you could share your mail ID on chat. And
Sure. I am happy to share my email ID. It is aniket.palkar@kpit.com. And I'm just also putting it on the chat right now. And I'm also happy to take any questions. I'm always, keen to particularly interact with students, and they always have, new ideas and, new things to be done in the industry, and we are always working on solving interesting problems. So I'm always happy to, take emails and answer, relevant questions, I would say, definitely related to
yes,
automotive industry and data science and data-driven intelligence.
sure. Great. Okay, then thank you very much, sir. Thank you for taking out this time. It was really a learning experience for all of us. Thank you all participants for joining in. We would end
Thank
the
you, sir.
session here and we would connect next week, same time with another topic, another speaker. Thank you, Aniket, sir.
Thank you, everyone. Bye.